Hi, hope you're well. So we've got this rendering finished off. We're finally going to get something. Spoiler alert, here it is. There it is. That's glorious. It's a triangle. Nice. So how does this work? Well, rendering, and anything really which happens in real time, is pretty much multi-threaded. If we're going to do multi-threaded things, we need to synchronize them. So it's time to have the talk. We're going to talk about semaphores. When we have multiple threads which are operating, they might share resources. But there's an issue with this because the threads don't know about each other. So a semaphore we can visualize as like a flag. Okay, so you've got a little section with your resource. You've got a flag there, and when a thread accesses the resource, it takes the flag. So the other threads, they see there's no flag there, they can't access the resource. When the thread is finished with its operation, it releases the flag or posts the semaphore, and then that's available for another thread to grab it. So there are two semaphores we're going to need. One to indicate that an image is available to render to, and another to indicate that a render has finished and we can present to the screen. So let's create those semaphores. It's really quite simple. The only thing we need to specify is that we are creating a semaphore, and then we can actually kind of create both semaphores in one line, or two lines here. And there it is. Okay, now we'll go to the drawing. Now I'll just take a big picture view first. So the first thing we're going to do is we're going to grab an image from the swap chain that we want to render to, and then we submit the command buffer that renders to the image, and then we submit the queue. We submit that image on the queue for presentation. Okay, there are a few more things involved in this though. So first of all, we call this acquire next image, and this flag here is the timeout in nanoseconds, and there's a trick. If we pass in the maximum 64-bit integer, then that is a special flag to say just don't timeout. Would kind of make more sense to just pass in -1 for no timeout, but hey, it is what it is. Now what this does is it acquires the next image from the swap chain, but it kind of spawns that process as an independent thread on the graphics card. So for that reason, this function call is quite quick. It just spawns another thread which does the work of getting the next image, and it's possible that we are continuing down through this work and we get to the next stage before this is actually finished. So we need to be careful about that. So we're submitting the queue. Okay, and we need to specify that we are waiting on the image available semaphore, and the stage which is waiting on that is the output. Okay, so just double checking everything. Okay, cool. So then we go along and we have this thing called a wait destination. So in OpenGL and Vulkan, the language of like source and destination is used a lot. So I've just written here, the wait source is the process which we've just come from before we start waiting, and the wait destination is the process that we're moving on to. However, it really doesn't make sense to have a wait source because we don't really care where we came from, we just care where we're going to. But this is just so that this really makes sense. Then, once this queue has finished, then the render is finished, and so we flag the render finished semaphore. That's signaled, it's released to show that we have finished rendering and that is ready to present to the screen. Okay, so then we go ahead and we submit that queue for rendering. Just a note here, I talked about it up here as well. We have semaphores and fences. Now, semaphore is a synchronization object which kind of works between individual queue families, and a fence is a synchronization object which works within the same queue family. Yeah, we're going to use semaphores for now. Okay, so that's all good, and we go and set up this present info, and that is waiting on the signal semaphores, which is the render finished, so we will not present to the screen until the render is completed. I'm going to work on the swap chain, and this is all self-explanatory. So then we submit this presentation info onto the present queue. Remember the present queue is the set of present instructions, the queue family. Okay, so that's all good. But there's one very subtle point that I need to add, and that is the subpass. So we go back to the create render pass, and we have this remember every render pass has by default one subpass, which in this case is pretty much just the color output, so rendering the color buffer, writing to the color buffer. Now there are kind of subpass transitions, subpass dependencies, and for the most part it's handled automatically, except that because of the multi-threaded nature of our program, we might grab the this thing might get out of whack, the render pass basically. So we might grab a render pass and start a render pass before an image has been acquired to render to. So for that reason, we have this thing. We have a dependency structure. Now the source is where we're coming from, which in this case is external, or not within our render pass. So this is the default, like before and after a render pass is completed. The destination is index 0, which is our standard render over here. Now the source stage mask is the variable that we're checking to proceed from the source subpass to the destination subpass. So we are basing this on the color attachment output, and that proceeds once the color attachment output bit goes to 0. In other words, we have an image, but that image has finished outputting its color to the screen, if that makes sense. So then we're ready to draw to that image. Do you see what I mean? We might grab an image and go to draw to it while it's still being presented to the screen. Hopefully that makes sense. Then we say, what are the conditions for moving to the destination stage? Well, it's based on the output bit, and we move on when that output bit is ready to write. So if we check all of this, really what we're saying is we're synchronizing everything up. So we only start drawing to an image when it's finished drawing to the screen, and we only proceed out of that once proceed out of that, what do I mean? Proceed to the render pass once we're ready to write to the color attachment. I hope this makes sense. Anyway, code's in the description. So all we need to do then is declare that we have one dependency and pass in a reference to the dependency as it's created above. Okay, so there's just a few things to note. In the draw stage, we go through this draw function, and then we have this line device wait idle, and that's just a synchronization thing. So if I close that off, let me run this again, check the memory usage on the right. We should see over time that it keeps increasing. And the reason for that is that the program is writing information faster than it's being presented to the screen, and it kind of builds up a backlog. Things are out of whack. Close that down, that's okay. I think if we run this again in release mode, it might be okay. Let's check that now. Okay, that seems fine. So I guess when we run it in debug mode, because it's outputting validation info and other things, it's a little bit slower, and it's just at that point where it's too slow to clear the buffer before it can go to the screen, and that creates the backlog and blows out our memory. However, that's not a great synchronization method, right? We can't just say, okay, make your computer faster. That doesn't always work. So for that reason, we draw the frame, and then we just wait until our device is all cleared and ready to go. And this is quite a basic kind of synchronization method. And in the next video, I'll be going through a more advanced method which uses synchronization structures to do it in a more multi-threaded way. Okay, anyway, I think I've talked enough. That'll be it for now. Have fun. Bye.